That is quite sad.
Questions? What? I will fix the slide.
What's the syntax there? Pick them up.
2, 4,
4. It should be 4.
This is the power set of n variables.
Any mistakes you find, please. We can use the teacher map for non-monotone disjunctions. If we want to learn a non-monotone function, we can use this feature map. Before we do a non-monotone disjunction, let's consider the simple case. Let's see how can we represent a monotone disjunction as a linear threshold function. Okay. So suppose I have five variables. Okay, x1, x2, x3, x4, x5, and imagine, I get some data. Maybe I get this is 1, this is -1, this is -1, this is -1, this is 1. This is a true example of this disjunction. So we'll say y is 1 there. If I had -1, -1, -1, 1, 1, this would be -1. This would be this example. The truth value is -1, so the outcome there would be -1. Likewise, if I had 1, 1, 1, 1, 1, the outcome would be 1. So where my disjunction is x1, x2, or x3, how can I represent this that I've represented logically as a disjunction as a function of the form sine u dot x plus b? What should u be? What should u and b take on? So what are values for u and b that would correctly classify these three instances or any instance of that disjunction over those 5 variables?
Quick question on your sine function.
Yes.
What's sine of 0?
It's just, for now, let's say it's 0. Okay. Maybe it should always round up or always round down. I'm not worried about that case. So u will be a vector. So u dot x is going to be equal to u1 times x1 plus u2 times x2 plus u3 times x3 plus u4 times x4 plus u5 times x5. What should u5 be?
0.
0. Why should, and I agree, why should u5 be 0?
Because its value can't affect the result.
Yeah, the disjunction has, the truth value has nothing to do with what's in the x4 or x5 position. So what should u4 be? Somebody else. Also 0. Okay. So what would be the linear threshold values then for, what values could we, for instance, then use for u1, u2, u3, and for b? Yes?
We can use everything 0 and u1 equals 1. And
Excellent.
b equals 0.
So we used u1 equals 1, u2 equals 1, u3 equals 1. So u is equal to 1, 1, 1, 0, 0. And then there's the question is, what should b be?
Or you could just select u1 equals 1 and everything else equals 0. And then b could be 0 as well.
I want it to work for every disjunction, that not just this data set.
Okay, okay.
Yeah, for this data set, you're correct. That would work perfectly.
B can be 0 here.
Plus 2?
Minus 2.
Yeah, it's something like -2 or +2. I guess it has to be, if we're adding 2 to it,
No, minus 2.
Plus
2 plus 2.
Change it.
it's b equals 2, because what's the worst case, for instance, would be this one, because so then we get this term contributes 1, this term contributes -1, because x2 would be -1, this term contributes -1, and so this summed up is -1, but we need to classify it positively, so we'd add a 2 to it. That gives us a 1. Likewise, it doesn't mess us up, for instance, in the all ones term, because then we'd get 3 plus 5, but the sign of 5 is still 5. So this would give us the linear classifier for this function. I mean, that's the linear classifier, linear threshold function form for that disjunction. Let me ask you a question. Suppose we did set b equal to 0 here. We'd still clearly be learning a linear function, but would this linear function be a disjunction?
First case.
Yeah, it wouldn't be a disjunction. It would just, we would predict what it's often called a majority function. You know, u1, we'd say it's true if the majority, if any 2 of these are true, or 3 of these are true. So, you know, disjunction is a nice concept. You know, you can imagine that, yes, you're likely to fall on the way to work if A, you haven't tied your shoes, B, you've drank a lot, C, you've just spun in a circle. That's a disjunction. But maybe if you're a really hardcore sort of person, you know, you really need 2 out of 3 of those conditions to be true before you fell on the way to school. Okay.
Can you explain? I don't understand why the b being 0 means it's not be able to.
Because if b is equal to 0, when will this be true? It'll be true if x1 is, if any pair x1, if any 2 of those or 3 of those are true. Because if all 3 of them are true, it'll certainly be more than 1. If 2 of them are true, it'll be more than 1. But if one of them's true, for instance, this is true and these are false, this will be -1. It won't be an example of it.
It has to be always. That's the point of it, right?
A disjunction is something that's true if any one of the variables in it are true. This example I've given is only true if 2 out of the 3 variables are true or more. Okay? So linear threshold functions can represent disjunctions, but they also represent more than just disjunctions. We saw this example of a majority function. Okay? If you're in computer science, you may have seen a number of these concepts before, but You know, we're interested in representing knowledge, you know, and not just learning smooth functions. A disjunctive normal form gives us even more representation than just a disjunction. What is the disjunction? This is a disjunction of conjunctions. It's an or of ands, okay? So for instance, you can imagine that with D and F, you can represent the concept of a cat. So what makes a cat? Well, if it's a house pet and it purrs and it has a tail, it's probably a cat. Or it doesn't have a tail, it's furry, has tapered ear and round eyes, one of these Manx cats. Maybe it's a cartoon cat. You know, I don't know, it doesn't necessarily have those other properties, but its name is Sylvester and chases a Tweety bird. So you can represent logical things with a DNF. And in fact, we'll observe quickly that all Boolean functions can be represented as a DNF. So how many, so suppose we're mapping from, let's say -1, 1 to the n, into -1, 1 to the n. How many possible Boolean functions are there? How many functions are there of this form?
Two.
How many Boolean functions are there? Yes?
Why is the code mean -1, 1 to the n?
What? What is this notation?
No, I mean, if it's a
Yes, thank you, because I've made a mistake.
well, it should be 2 to the power of 2 to the n.
Perfect, yes, sorry for confusing the issue, yes. So there's 2 to the n Boolean functions. And so here I'm going to, so what does a Boolean function look like? Well, we have to give a label to, for instance, these three things. I'd have to give, you know, I have the case where x1 is true, x2 is true, x3 is true. I have the case where x1 is true, x2 is true, x3 is false, down to x1, x2, x3 is false. And I have 2 to the n cases, and I have to give a truth value to each of these cases. So there are 2 to the n possible functions. And a way to think about any given Boolean function then is as a coloring of the hypercube. So imagine I have an axis for each of my Boolean functions, and so maybe I think red means true. Maybe I'll make green false. I'll make, so green's false, red is true. So how many ways can I color this hypercube's corners? 2 to the 8 ways of coloring the hypercube's corners. And so if you look, every DNF function, all I have to do is include that, to represent this function as DNF, I have to include as my disjunction not x1, not x2, not x3. Or x1, not x2, x3. So this function is, if I have a given DNF, I can just simply represent the places where it's true by including those terms for the DNF. So any Boolean function corresponds to some DNF with up to 2 to the n terms in it, where each of those terms corresponds to me naming a corner of the hypercube. And then if we think about linear threshold functions, they kind of, represent some subspace of this Boolean hypercube. Okay. So DNF learning, you can represent any Boolean function. It's kind of a nice way for representing knowledge. Basically, we know a lot about it, but there's lots of unsolved major open problems in machine learning on what sense we can learn DNF from data. But where we're going is we're going to look at learning DNF with linear threshold functions in a feature map. Questions? Okay. Okay, so instead of you can think of this as learning a disjunction of experts instead of learning a single expert. Okay. So we have a way of learning disjunctions already, k-monotone disjunctions. One way to do that would be to just use the halving algorithm. Okay. Suppose we wanted to learn the best k out of n literal disjunction. Okay. Well, what we would do is we can now create an expert for each of those n choose k literal disjunctions. Okay. Now, if we were running that exactly, that means we have n choose k disjunctions, and we could learn exactly log of n choose k, or we could go ahead and weight it if we assume that some disjunction is inconsistent on some of the data. And we get a pretty good bound. The number of mistakes of our algorithm, the noise-free case is roughly k log n over k, where k log n over k is roughly log of n choose k. But the problem is, of course, is if we have n, this algorithm, as we said, it's great. We can use a halving algorithm, the weighted majority algorithm, to combine a lot of algorithms and get a good balance. The problem with that is, how do we implement it efficiently? If we're going to have n choose k weights, we have weights which are exponential in k. Okay? So we're going to look and see how we can do this efficiently. Yes.
The difference with before is now we have weights per disjunctions, and before we had weights per experts.
Our experts are disjunctions now. So now, suppose you wanted to learn a k-literal disjunction. So you would, how many possible k-literal disjunctions are there? N choose k now. And so each expert will predict as one of those disjunctions. So you imagine we have, suppose we're learning 3 literal disjunctions, maybe, and so k is 3, n is 7. That means we need 7 choose 3 experts. Where these experts just correspond to all possible disjunctions of size 3 from 7.
Are the sole experts still experts, or only the disjunctions?
The experts are the disjunctions.
Is a single term a disjunction?
So let me make it quite concrete. Okay, so imagine we have disjunctions with 5 variables, okay? And let's say we're trying to learn a disjunction of size 2, okay? Our experts then will be the following. Our experts will be x1 or x2. Another expert will be x1 or x3. Another expert will be x1 or x4. Dot, dot, dot. x4, x4, or x5.
Okay.
How many of there are these? There's 10 of them, I guess. Okay. Each of these experts, when it sees, for instance, this line of data, this one will go, is 1 or -1 true? This expert will predict on this one. It'll predict, yes, that's true. This one will also predict it's true because 1 is true. And for x1 will also predict that it's true. We'll pretend that I have a -1 here, and this one would predict -1.
And why do we choose disjunctions and not conjunctions?
On one level, it's arbitrary. Disjunction is, we could think of using conjunctions for representing things instead of disjunctions. And almost everything I say before has a parallel form and bound in the conjunction world. Disjunctions for us are more natural for 2 reasons. One, a disjunction already looks more like a linear threshold function because, when you do that dot product, you're summing things. When you're summing things, numerical sum is like logical OR. Okay? So linear threshold functions are already kind of set up naturally for learning disjunctions. The second reason is it's disjunctions, I don't know, I would argue are maybe a slightly more natural concept class than conjunctions in terms of, it's not always more natural, but in many cases what you're interested in is you have some high dimensional data, maybe you have microarray data, and you want to make some prediction, and that prediction is going to maybe depend on a few variables. And the question is it depend on if any one of those variables is true, or if all of those variables are true? I don't know, disjunctions tend to come up more in practice, but there's a parallel to what we say in the conjunction world. Other questions? Those are good questions. Okay. So one way to learn K-literal disjunctions is we use this trick that we know that we can just create a large set of experts which predict like disjunctions. The problem is to form these predictions will take n choose k time, which, if k is anything large, it's quite slow. Okay, exponential k. Other questions? Okay. We'll come back to that, but an easy algorithm to learn linear threshold functions with and then go from linear thresholds to disjunctions is the Perceptron algorithm. Okay. So let's look at how the Perceptron algorithm works. So the idea of the Perceptron algorithm is we have some instances of data, we have some negative instances, some positive instances, and they're separated by some line. And we want to learn a line that classifies them perfectly. Okay? And just like you did with the SVM, you tried to find the line that maximized the margin between the positive and negative examples. The Perceptron algorithm is an online algorithm. It's not going to find this line that maximizes the margin. It's going to find any line that separates the examples. But the line it finds will have a guarantee in terms of how big the margin is on the examples. If you have a data set which has a large margin on the example, somehow it's easier to learn because things are less close together and you're less likely to confuse them. Okay? Okay, let me continue. So G will be our notation for the size of this margin. V will be the normalized classifier that predicts the examples correctly. So as you see, this vector V will predict for us. Okay, we're going to assume that's of size unit 1. Okay, so we're an example will be some x and y. For us, we're going to assume that y is -1 and 1. X is, we're going to think about beyond just learning Boolean functions. They're all going to lie in some radius r. Okay? And the assumption on the classifier that we find eventually is that it's going to classify the examples correctly with some margin g. Where this margin g will be x dot v. So what does this notation mean? So x dot v is our prediction y hat. Y will be our label. So if x dot v is a positive number and y is a positive number, we've correctly classified. If y is a negative number and x dot v is a positive number, we've incorrectly classified because y and y hat don't match signs, and so it won't make our assumption. If they're both negative, likewise, we'll have classified correctly. So we want to classify correctly, but with some margin g. Okay. Perceptron algorithm works as follows. Examples are going to be presented one by one. Our initial guess at a classifier will be W0. W dot x will be our prediction. Whenever we make a prediction, it's a mistake if W dot x doesn't match the sign of y, so that has to be less. It'll be a mistake if that's less than 0. And what we do is we do a corrective update. We make a mistake. We simply add on to wi. That should be small xi, the value of our instance. Okay. So let's look at how the Perceptron algorithm works. So we have a point which we're going to predict. That's the easiest to go through. Okay, so far we've learned this hypothesis. We see the red point here. We need to classify that as a negative, but our decision plane looks like this so far. So we've made a mistake, and so we now need to update the hypothesis in this direction. So we added the negative on that example to our hyperplane W. That changes the direction of W. And now we see that after we've done that, we're now correctly classifying these minuses and this plus. Okay, so that's kind of the intuition behind how the update works. Let's look at how we prove an upper bound on the number of mistakes that the perceptron can make. So the number of mistakes we're going to find for the perceptron is it's bounded by the radius in which the space lives. So the larger xt's can potentially be, the larger the bound will be. The larger the margin, the g, the fewer the number of mistakes will be. So and the way this proof will work roughly the same sort of proof that we already did on weighted majority. Somehow we're going to work by combining upper bounds and lower bounds and use that in our proof.
What is R?
R is the maximum norm of the x instances. Okay, so if they were if they're in this example of binary instances like this, what would be R then in that case? R would just be the square root of n, because we sum up each of these squared. There's n of those. That gives us n square root of n. So with binary instances in the 1 minus 1 form, R would work out to be the square root of n. Okay. So once more, we're going to look at how things change when we make a mistake. So we have the following observation. If we've made a mistake, i.e. the sign of wi and xi is different than y, then we know that the squared norm of wi will be less than this. Let's see why that's the case. It just comes from squaring out this term. So wi plus 1, by the definition of the update, is equal to yi plus yi xi. What is wi plus yi xi squared? That's wi squared plus xi squared minus 2wi yi xi. We know that's negative, and so we can drop that and bound by the positive terms. Okay, so we're just leaving out the middle term, which would be twice that because that's negative. So after I mistakes, the upper bound on wi squared is I times r squared. How can we prove that? Whenever we make a mistake, we're just adding on xi squared. Xi squared is no more than r squared. Okay. So we're adding on up to I terms whose upper bound is r squared. So that gives us an upper bound on wi. Now we can also get a lower bound on wi. So how do we get a lower bound? So wi we know will be more than wi dot v. V was assumed to be 1 in our first slide. And so A dot B doing this backwards. Yeah. A dot B is always upper bounded by the norm of A times the norm of B. This is the Cauchy-Schwarz inequality. So if V is 1, we know that this is the norm of Wi is bounded by W dot V is upper bounded by the norm of Wi. Now we're going to prove a bound on Wi dot V of IG. How do we prove that? Whenever we make a mistake, we have that. Just check, sorry. So on each trail we make a mistake, Wi becomes Wi plus Xi times Yi, because this is our update. We can separate that into two terms. So we get Wi dot V plus Yi Xi dot V, just separating into two terms. How many times do we do this? We do this I times. And we also have the assumption that we always separate with a margin of G, because Xi dot V is always more than G in our original assumption. We assume that for each, that X dot V is more than G. So we can now combine the two bounds. So the total number of updates, which on the previous slides I was listing as I, I'll now list as G. So we have the lower bound of I times G squared and the upper bound of I times R squared on the final weight. So Wn is bounded by m squared g squared divided by m squared r squared. So we can divide out both sides to get that the number of mistakes of the perceptron is upper bounded by the radius divided by this margin squared term. So there's more than one way of thinking about what the perceptron is doing. So instead of thinking of that we separate with a margin of g, an alternate way of viewing what's going on is that we're learning a predictor u which separates with a fixed margin. So not changing the algorithm in any way, just changing the analysis. V was any predictor that separated with a margin of g. Now we're defining a predictor u, which is just v times g. The algorithm doesn't use u or v. These just come up in our analysis. So I can substitute in the previous analysis v over g for u, and then we can write this bound as m is bounded by the radius of the data squared, the radius of the predictor that fits our data, with a margin of 1. So I just divided through to get this. This other form is kind of a nice way to think about what's going on, in that u squared now you kind of think of the norm of u as a measure of the complexity of your predictor u. Questions so far? Yes.
What happens if the class is not linearly separable?
So if the class is not linearly separable, two answers. One answer is you can prove a type of bound on the number of mistakes that the perceptron will make. It will, of course, this bound has to depend on the number of mistakes of the best predictor. So you can prove a bound, but you might want to change your algorithm in some way so that you converge to something reasonable. But that's kind of and there's a lot of proposed algorithms for that, but that's beyond the scope of what I want to do. Have to assume that it's linearly separable. I mean, there's certain things you can do to force your function to always be linearly separable.
If it's not that complex, so you have overlapping samples, but just like a slight curvature, and so that you can approximate it with something linear, but you will certainly have some points on the wrong side.
So this is a standard exam question. Maybe not in that form, but so basically by using a feature map, you can force it to be linearly separable. Where, roughly speaking, right now, let's say you're just working in Rn and your dot product is u dot x. Somehow, if you add on to your dot product a term that looks like gamma I xi for a how do I describe how to do it easily?
Sure makes the exam look easy.
I mean, the easiest way is with so let's look at what happens with the perceptron if it's not linearly separable. So suppose your goal is to find something that separates your data or separates some approximation of your data. First observation with the perceptron is you run it through and it gives you a bound on the number of mistakes, but it doesn't find a linear separator necessarily. Okay. If you keep cycling the perceptron, you can then, it must eventually find a linear separator if there is a linear separator, because on any trial where you don't make a mistake at all, the algorithm will have converged. It's not going to change, and so therefore it's linearly separable. If it's still making a mistake on a given epoch, you have an upper bound on the number of epochs it can run, which is just this mistake bound. So the perceptron will eventually find a linear separator if you keep cycling it on your data. So then the question has, well, what happens if you keep cycling on your data and it's not linearly separable? So there's a lot of things
Like
you can
fluctuates.
do. What?
It will fluctuate.
It'll fluctuate, it won't converge, but you can force it to converge. And the way you force it to converge is the following. I think there's lots of ways to describe it. I'm just trying to think what's the easiest way to think about what's going on. So let's say our data is n-dimensional. So we have x1 dot 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 x n, and we have some m data items. What we can do is we can do a feature map. So the feature map would be, so now let's call these, I don't know what to call these, I'll call these delta 1 dot dot dot. If we know our data set is size m in advance, okay? Let's just assume we know the size of our data set, okay? If we know the size of our data set, then we can add on to whatever, so here's what our x1 instance, we leave in our normal instance, but then we add in 1 0 0 0 0 dot 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 0 0 0 0 1, where this is in the nth position, 0 1 0 0 0. One type of C's here. So we have this feature map, which I don't know what to call it. I'm going to just call it phi, since I'm doing this off the top of my head. Okay, phi of C. I claim in this feature map, our data is now linearly separable. Can you give me an argument why, using this feature map, we now have linearly separable data? That's a 0 here. What's a linear separator for this data? Assuming this is non-separable by itself. How do we know it now separates?
Its data point lies on an axis, the different axis. Now.
Can somebody give me a separator? I think you have the right idea. Well, a linear separator now would be, one example separator is, we just leave these at 0, ignore this data, have this correspond to label, this n plus 1 would be whatever the sign is of the label. If our label is -1, then U1 here should be -1. If label U here is positive, it should be positive. What we're doing then is, it's like we have an additional identity matrix which we're adding on to our vector, and we're separating on the basis of this identity matrix. Okay?
So it's a diagonal in that space.
Yes, so it's just like, it's the same thing that you'd often do with a positive semi-definite matrix. If you want to ensure it's invertible, you add a little bit to the diagonal. The larger you make this C, the more you're ignoring this data here. But it'll always separate. The smaller you make C, the more you're kind of trusting this to separate.
What are you doing with this feature map? It maps x's to?
It maps x's to itself, and then it adds on m more variables.
So it takes
X
x
maps,
and it adds a
it
delta.
takes phi of x maps x to n plus m dimensions, where the first part of it is just x itself, and the second part corresponds to the unit vector for what item number it was in your data set.
It's as if putting them in different planes, or
You're adding m new dimensions such that you can always separate in these m new dimensions, and you're forgetting about what's going on here. If you make this really large, it's completely pointless. You're not learning anything at all. You're going to get perfectly separable data that has very little connection to your x's. Even if you make these c's arbitrarily small, you'll eventually separate. It may take a long, long time to separate, but you'll eventually separate, and hopefully you'll see some trade-off between x and delta. I mean, you can prove more about the function which then separates using this trick.
Aren't feature maps only practically helpful if you can back to the original number into the original space, or?
Feature maps are helpful. You want to learn of some function that's not linearly separable. Lots of functions aren't linearly separable. That's why they're helpful. I didn't understand your question.
Kind of
That wasn't the
notion
best answer.
Sorry, I'm struggling with the notion that you add m new variables into the model
Yes.
and then use those instead of the data.
Well, you don't want to use these. That's why you set the diagonal very small.
So C is very small.
Yes, C should be very small. If you want it to converge extremely fast, set C very large, and it'll converge extremely fast and it'll have no connection to your data at all. You set C very small and your data is almost separable, then there will be some connection. Okay, we can quantify this, but I'm not up to quantifying it on the top of my head at this moment.
So going back to the original thing on the perceptron algorithm, we're assuming the hyperplane goes through the origin, the separated
Yes.
hyperplane at this point.
Yes, we're assuming the hyperplane goes through the origin. So what we're doing with Boolean functions, and the trick that we always use, if we want to make the hyperplane not go through the origin, we use a feature map. We add on a bias term, okay, where that bias term is some constant, okay?
Right. Just ones would do. I mean, anything, yes.
Yes, but once more, the value of the constant does affect the learning. Okay.
As always.
So you set it too small, and it's going to be very hard to learn that threshold. Set it too large, and you're fighting against your threshold. Yes, all our techniques that we've normally given, well, the way we've done linear regression, the way we're doing the perceptron, the way to get a bias is to add on an additional term to your data. Depending on how your SVM is implemented, some SVMs, the traditional definition of an SVM doesn't require you to add on a bias term, that finds it without you adding that into your data. some SVM implementations, because they solve the optimization in some way, require you to add in a bias term. Yes?
Again, but I still cannot see how you can turn your non-linearly separable data into linearly separable data and still preserve the structure of the data. It seems so arbitrary.
If your data in some sense is completely non-separable, of course you're kind of right in some sense. There's nothing that you're what are you doing when you do this? You're allowing yourself to fit the noise a little bit, and if C isn't too large, you're not changing your predictions here very much if you almost learn to fit.
What about other transformations? For example, if you have data that are not linearly separable, but you can squeeze a quadratic function through them.
And then the Perceptron algorithm, as we've presented it, you observed I've had pluses, I've had dot products. I've done nothing with the Perceptron that doesn't mean I can't use it with the kernel function. So if I can use it with the feature map, that feature map corresponds to a kernel, it's fine. So I can throw in a Gaussian kernel.
What's the difference of using a kernel and doing that thing there?
And doing this feature map?
Yeah.
It's just a computational difference. That's all. I could write this as a kernel function where now it would be something like k of, if I wrote this as a kernel function, I'd write it as k xi xj is equal to the inner product of xi dot xj. Then I have these terms. These terms are only going to contribute if I and j are the same, i.e. when I do the dot product between xi and xj, if they're not equal, this term contributes 0. So this corresponds to plus c squared, I'll use this notation, where delta ij is only 0, is 0 if I doesn't equals j, and is 1 if I equals j. Okay? So this is the feature map, the kernel. So the kernel map between xi dot xj is equal to, and it's just equal to this. I'm doing the normal dot product between the things, plus I'm adding a little bit if I'm ever dotting an element with itself.
What's the delta there?
Delta is 1 if I equals j.
It's the product is delta.
Yeah, but I've kind of written it as 2 arguments, but okay. It's just the notation. Other people write this as I changed the notation, I'm sorry.
Yeah, it's also good.
Okay. So this kernel is the same as that. As you see, if C is small, you have almost the same inner product. If C is large, the inner product is changed when you're dotting something with itself. Okay, questions? Very good questions. I like your questions. They get to the meat of the matter. If there's no more questions, let's take a break for 10 minutes.
I'm gonna go get some more as well.